Hello everyone, I am Om Krishna Gupta. I am assistant professor in electronics and communication engineering department in Ajay Kumar Garg Engineering College, Ghaziabad. So, this is lecture 12 of the subject analog circuits. In this class, I am going to discuss high frequency response of CS amplifier and low frequency response of CS amplifier, that is common source amplifier. So, before this class in lecture 11, I had discussed about the frequency response of CS amplifier. So, in that particular class I had discussed that the voltage gain of the common source amplifier or common emitter amplifier in BJT, the gain is not constant for all frequency. The gain is reduced at low frequency, the gain is reduced at high frequency. Reason I had explained in the last class. So, the point is that when we draw the frequency response of common source amplifier or common emitter amplifier, then what happens? In frequency response, on x axis there is a frequency, on y axis there is a voltage gain in dB. In dB means 20 log mod of V naught upon Vin. V naught upon Vin is the voltage gain in ratio, and to convert that ratio into dB, then we take log and multiply with 20. So, the frequency response is like this. So, we can see that at high frequency the gain is reduced. The gain is reduced due to internal capacitances, that is also called parasitic capacitance. And at low frequency the gain is reduced due to external capacitors. External capacitors, for example, coupling capacitors CC1, CC2 and your bypass capacitor. So, whenever we connect the external capacitors CC1, CC2, bypass capacitor, then gain is reduced at low frequency. And for all amplifiers, whether it is discrete circuit amplifier or integrated circuit amplifier, the gain is reduced at high frequency. Reason is that if we are using transistor, whether it is BJT or MOSFET, there will be some internal capacitances formed inside that transistor. So, at high frequency the gain will be reduced. So, I had explained the reason behind it, that why at high frequency the internal capacitance play an important role and why at low frequency these coupling capacitors play an important role. Fine. So, what we have to do here? We have to calculate the bandwidth of this common source amplifier, bandwidth of common source amplifier. And how we calculate the bandwidth? To calculate the bandwidth, we find out the upper 3 dB frequency, that is denoted by FH, and lower 3 dB frequency, that is denoted by FL. This FH is also called the corner frequency, upper corner frequency and lower corner frequency. FL is lower corner frequency, and the difference between FH and FL is called the bandwidth of the amplifier. So, to calculate the bandwidth of the amplifier, we need to calculate the value of FH and FL. Once we get the value of FH and FL, then we can calculate the bandwidth of the amplifier. And once we understand the process for the common source amplifier, the process is similar for the common emitter amplifier also. So, that is why we are going to study firstly the high frequency response and then the low frequency response. The objective is to calculate the value of the FH and FL in order to calculate the bandwidth of the common source amplifier. So, to calculate the value of the upper cutoff frequency, that is called FH, this FH is also called minus 3 dB frequency. This is called minus 3 dB frequency because it is the frequency at which the gain is reduced by 3 dB of the maximum gain. For example, if the maximum gain is 50 dB, for example, the maximum gain is 50 dB, then at frequency FH and FL, at frequency FH and FL, your gain will be 47 dB. So, FH is defined as upper minus 3 dB frequency, FL is lower minus 3 dB frequency. So, there are various names, upper minus 3 dB, lower minus 3 dB, upper corner, lower corner, upper break frequency, lower break frequency, all are same, terms are same, but the definitions for all the terms are same, fine. Terms are in fact different, terms are different, but the definitions are same, fine. So, your FH and FL are the frequencies at which the gain is reduced by 3 dB of the maximum gain. Now, see, if we want to calculate the value of FH, then of course, we are going to study the high frequency analysis. In high frequency, the internal capacitances play an important role, fine. Why it is so? So, please refer lecture 11, in that class I had discussed that why due to internal capacitances the gain is reduced at high frequency and why at low frequency the gain is reduced due to coupling capacitors, fine. So, obviously, if we are going for high frequency response, it means that we are considering that the coupling capacitors and bypass capacitors are acting as a perfect short circuit. We are not we have not included those capacitors because that those capacitors are not effective, because those capacitors, your external capacitors, coupling capacitors and bypass capacitors are acting as a perfect short circuit at high frequency, fine. So, there is no coupling capacitor or bypass capacitor in high frequency model. In high frequency model, we consider the internal capacitances. So, I had also discussed about the internal capacitances in the last class. So, there are various internal capacitances formed in the in MOSFET, fine. So, out of those internal capacitances, two important internal capacitances are your gate to source internal capacitance and gate to drain internal capacitance, gate to source and gate to drain, and we are neglecting the body effect. Now, Vsig is the input signal and the internal resistance of Vsig is Rsig, Rg is your gate resistance, that is very high, and your CGS, that is connected between gate and source, CGD is connected between gate and drain. This is your controlled source, dependent source, R naught is the output resistance. We consider R naught when we consider the channel length modulation effect. In discrete circuits, we can neglect R naught, but in IC amplifiers, in IC designing, this R naught plays very important role. Rd is your drain resistance, RL is the load resistance. So, these things I had discussed in the last class also in the high frequency model of the MOSFET. Now, see, we can simplify this high frequency model just by using Thevenin equivalent. In Thevenin equivalent, we can see that if we remove this Vsig, it means short circuited, if we short circuited this Vsig, then your Rsig and Rg, it will be in parallel. So, we can replace Rsig and Rg with a single resistor, that is R dash sig. This R dash sig, it is the parallel combination of Rsig and Rg. So, similarly, corresponding to this, what will be the new value of V dash sig as per Thevenin equivalent? It will be Rg upon Rg plus Rsig into Vsig, fine. Now, see, at the output side, since we can see that this R naught, Rd and RL, these resistors are in parallel. So, to simplify it, we have replaced these three resistors with a single resistors, that is RL dash. This RL dash is equal to R naught parallel to Rd parallel to RL, fine. Now, coming to the calculation part, we can easily calculate the midband gain V naught upon Vsig. We have already calculated it in unit 1. In unit 1, we have calculated the overall voltage gain, that is Gv, and here that Gv is represented by Am, that is the midband gain, and we have calculated this expression. We had got this expression, but the point is that this expression we get when we do not consider Cc1, Cc2 and Cs, coupling capacitors and bypass capacitors. When we do not consider these capacitors, then we get this midband gain. So, we have seen that in midband the gain is constant, the gain is highest, fine, because in midband there is no capacitive effect, there is no capacitive effect. So, this expression we have already derived in unit 1, and by this high frequency model we can write the value of V naught, that is minus of Gm into Vgs into RL dash. Minus sign is coming because this is the common source amplifier, fine, and RL dash is R naught parallel to RD parallel to RL. Now, what is the value of IGD here? IGD is the current flowing through CGD capacitor. Now, see what will be the value of IGD? It will be equal to, you can see that at the gate terminal the voltage is VGS and at the drain terminal the voltage is V naught. So, simple, the current flowing through CGD, it will be the voltage difference across this CGD, that voltage difference is your VGS minus V naught upon this CGD. And what is the impedance of this CGD? That is 1 by S CGD, fine. So, we can write the expression for IGD, the current flowing through the capacitor, that is equal to the voltage difference across this capacitor upon the impedance of the capacitor, and remember that the impedance of the capacitor is 1 by SC. Here this the C is CGD, gate to drain, fine. So, by doing this we can get the value of IGD, that is SCGD into VGS minus V naught. Now, you can see that we have already calculated the value of V naught, just write the value, just put the value of V naught in this equation and just simplify the expression. After simplifying we get the value of IGD, fine. Now, see one more important thing here, just refer this high frequency model of common source amplifier. How the circuit will come to know about the existence of this CGD? It will come to know about the existence of CGD because of this current IGD, fine. So, we can replace this CGD with another capacitance called C equivalent, that is connected between gate and source, with the condition that the same current should flow through this C equivalent, fine. So, the point is that the existence of CGD will come into picture only because of this IGD. So, we can replace this CGD with C equivalent connected between gate and source, that is gate and ground, because because the source is grounded, with the condition that the same current should flow through this C equivalent. So, we can write it like this. Already we have calculated the value of IGD, current flowing through CGD. Now, the current flowing through C equivalent, it will be equal to VGS upon impedance, capacitive impedance is 1 by SC, that is SC equivalent. So, it can be written as SC equivalent into VGS. Now, the point is that the capacitor which we have connected here, that is called CGD, now this capacitor CGD is replaced with another capacitor C equivalent, and the current flowing through the C equivalent is your IGD, fine. The current should be same, only then we can replace it, fine. By doing this we get the expression for C equivalent, that C equivalent capacitance, that is equal to CGD into 1 plus GM RL dash. So, the point is now the equivalent input capacitance is increased by the factor 1 plus GM RL dash, 1 plus GM RL dash. Now, see the value of CGD, the value of CGD is small, the value of CGD is small, the value of CGD is small. Why? Why? Because in saturation region the channel is pinched off, because of that the value of CGD is very small, but when this CGD is connected between two nodes and across two nodes, if the gain is high, then this CGD will get multiplied by a larger amount, that is called 1 plus GM RL dash. Now, you can see that this CGD is connected between gate and drain terminal, and in common source amplifier input is applied at gain and output is taken from drain. So, whenever a capacitor is connected between two high gain nodes, then in that case the value of the input capacitance is increased by the amount gain 1 plus GMRL dash, although GMRL dash is very higher. So, sometimes we neglect this one also, fine. So, the point is that this is called Miller effect. This is called Miller effect. Miller is the name of the scientist. So, in Miller effect what happens, your capacitance CGD that is connected between gate and drain, it is increased by the amount 1 plus GM RL dash. It is increased by the amount 1 plus GM RL dash. This factor 1 plus GM RL dash is called Miller multiplier. It is called Miller multiplier, and this effect is called Miller effect. So, the point is that due to this Miller effect, the input capacitance it is increased. It is increased because you can see from the model, now the input capacitance it will be equal to, seen will be equal to your CGS plus C equivalent, CGS plus C equivalent. Now, your C equivalent is very high because of the multiplication of the factor 1 plus GMRL dash. So, the input capacitance is increased because of this Miller effect. Now, we can rearrange the terms and we can get easily VGS is equal to Rg upon Rg plus R sig into V sig into 1 upon 1 plus S upon omega naught, where omega naught is the corner frequency. Now, you can get this equation very easily, just refer this diagram. Now, from here you can calculate the value of VGS very easily. VGS will be equal to, by using voltage division rule, it will be the total capacitance upon total impedance, that is R dash sig plus total capacitance. So, from here you can get the value of VGS, and obviously in that expression of VGS we will get this impedance of the capacitor, and the impedance of the capacitor if we are including, it means that there will be S factor. Now, what you have to do? You have to just calculate the value of VGS using voltage division rule and rearrange the terms, and after rearranging the terms convert the equation in this form 1 upon 1 plus S upon omega naught form, where omega naught is the corner frequency, it is also called break frequency or pole frequency, and this omega naught you will get 1 upon C into R dash sig, where C is total input capacitance, that is the summation of CGS and C equivalent, and the value of C equivalent is CGD into 1 plus GM RL dash, and R dash sig is R sig parallel to RG, R sig parallel to RG. From here we can calculate the overall voltage gain, that is V naught upon V sig very easily. Now, see, now the previous equation can be replaced with the help of this equation, where AM is the midband gain, which we have already calculated in unit 1. The midband gain is basically the gain which is achieved in the mid frequency in which there is no capacitive effect, fine, and omega naught, that is the corner frequency, that is 1 upon C into R dash sig, omega h, we can write omega naught as omega h, upper 3 dB frequency, higher cutoff frequency, that is also called. Fh will be equal to omega h upon 2 pi, that is 1 upon 2 pi C into R dash sig. Now, see here one important point. In common source amplifier, your Cin is increased, because of that your Fh is reduced. This Cin is increased because of the Miller effect. Due to that Fh is reduced, due to that the bandwidth of common source amplifier is reduced. That is the drawback of the common source amplifier, that is the drawback, and the bandwidth is reduced because of the Miller effect. So, this point I have already discussed, that your Cin is increased, that is why your upper 3 dB frequency is reduced, and there is one more term in this expression of Fh, that is R dash sig. And what is this R dash sig? It is the summation of R sig parallel to Rg. Since Rg is very large, so we can write it R dash sig is approximately equal to R sig. R sig is the internal resistance of the input source. So, if the internal resistance of the input AC source is more, even then your Fh will be reduced. So, we have to be careful about it, fine. So, I have already discussed this Miller effect, the factor this 1 plus GM RL dash is called Miller multiplier, and due to the increase in input capacitance the bandwidth is reduced. So, this is the high frequency response of CS amplifier. In high frequency response we can see that the gain is reduced at high frequency, and because of the pole we are getting here, that is why the slope is minus 20 dB per decade. So, from here it is clear that at high frequency the gain is reduced because we are getting the pole, and this is a kind of STC circuit of low pass type. STC, that is single time constant, STC is the circuit in which there is a one resistor and one reactive element, it may be a capacitor or inductor, and generally it is divided into two parts, low pass and high pass. This is a kind of low pass type. Now, next one is low frequency response of CS amplifier. In low frequency response, now there is no effect of internal capacitances. Now, the external capacitance come into picture, coupling capacitors and bypass capacitors. Now, we can draw the small signal model. In a small signal model, the DC sources are removed, that is why your current source will be open circuited and your DC sources, DC voltage source will be short circuited. So, you can see that this is the small signal equivalent circuit, and the small signal analysis has been directly performed on the circuit. Now, what we have to do in low frequency response of CS amplifier, since there are three capacitors, and due to these three capacitors we will get three corner frequencies. Now, what we have to do? We have to calculate the corner frequency due to individual capacitor. What we need to do? Firstly, we will consider CC1, and we will consider that in that case CC2 and CS are perfectly acting as a short circuit, fine, when we consider CC1. Then we will see that due to CC1 what is the corner frequency. Then the second case is, now we take the case of CS, bypass capacitor. In that case we will calculate the corner frequency due to CS. Then in the third case, due to CC2 we will calculate the corner frequency. So, we will get three corner frequency in this case, and we have to firstly calculate these three corner frequencies. To calculate these three corner frequencies, now we can get the expression of Vg here, the gate voltage here, just see to it, the gate voltage Vg, we can calculate it with the help of voltage division rule. It will be Rg, your Vg will be equal to V sig into Rg upon total. Total means Rg plus R sig plus CC1. The impedance of CC1 will be 1 upon S CC1. This is the value of Vg, one important thing. Second thing, when we consider CS, bypass capacitor, then we can calculate the value of drain current Id. The drain current Id, it will be equal to Vg upon the source resistance is 1 by Gm plus the impedance of CS is 1 by SCS, fine. This is the value of Id. From here we will get the second corner frequency, fine, and the third corner frequency we will get due to this CC2. To calculate the third corner frequency, we will calculate the value of I naught. With the help of I naught, we will calculate the value of V naught. From there we will get the third corner frequency. Now, see, here we will use current division rule to calculate I naught. This I naught is basically minus of Id. So, we can calculate it with the help of current division rule. In current division rule, what happens? Opposite branch upon total. This is the process actually what I have described. Now, you have to just do the calculation and calculate the corner frequencies. Now, the first corner frequency we can get here from this expression. Now, what we have to do? We will get the expression in the form of S upon S plus something. S upon S plus something is the kind of high pass. It is a kind of high pass, fine. So, from here S upon S plus something, this something is basically your corner frequency. So, the first corner frequency is 1 upon CC1 into Rg plus Rc. Similarly, to calculate the second corner frequency, we will use this expression of Id that I have already discussed. From here we will get the second corner frequency, that is Gm upon Cs. Again it is the form of S upon S plus something. This something is your corner frequency. This is a kind of high pass type. Similarly, to calculate the third corner frequency, we will calculate the value of I naught here. Now, one thing we need to modify here is, this is actually not I naught equal to minus Id. It will be I naught equal to minus Id into equivalent impedance. that is opposite branch upon total. So, here we will get this I naught expression, from there we can calculate the value of V naught, and again it is in the form of S upon S plus something, this something is your third corner frequency. Now, we can see that out of these 3 corner frequencies, the highest frequency is omega 2, because in omega 2 expression we are getting Gm upon Cs, Gm upon Cs, fine. So, this is the overall expression V naught upon V 6, that is the overall gain, and you can see that there are 3 corner frequencies in this expression, and this particular term is called midband gain, and midband gain we have already calculated in unit 1. Now, after that, this is the low frequency response. In low frequency response, the gain is reduced at low frequencies. Since there are 3 corner frequencies, that is why firstly there is a slope of 20 dB per decade, then 40, then 60, because there are 3 corner frequencies, and the highest frequency is second corner frequency, that is Fp2, because there is a transconductance terms in the numerator and the transconductance of Cs amplifier is higher, that is why it is the highest frequency, second corner frequency. And if Fp2 is sufficiently larger than Fp1 and Fp3, then sometimes we neglect this Fp1 and Fp3 also, fine. So, point is that if Fp1 and Fp3 is very small, then the lower 3 dB frequency it will be equal to Fp2, fine. The reason I have already explained. So, the point is that how we calculate, how we determine the pole frequencies, first reduce V6 to 0, then consider each capacitor separately and assume that the other 2 capacitors are acting as a perfect short circuit, and for each capacitor find out the total resistance seen between its terminals. So, by using this process we can determine the different corner frequencies, different cutoff frequencies, corner frequencies, break frequencies, and the main design objective is to place the lower 3 dB frequency at a specified value while minimizing the capacitor value. We have to be careful, because FL is Gm by Cs. Now, if we decide FL, then corresponding to that obviously we will select the value of Cs, and obviously we want that the value of the capacitor should not be larger, because it occupies more area, So, this is there is a trade off, in fact, when we decide a value of FL, then corresponding to that accordingly we select the value of Cs, and this FL plays the role in calculation of the bandwidth. That bandwidth is FH, that bandwidth is upper 3 dB frequency minus lower 3 dB frequency, fine. So, that is the design parameter. So, this is the reference, and in this class I have discussed the high frequency and low frequency response of Cs amplifier.